Hello everyone, my name's Joseph. I work at PlayStation. Give you a bit of background on my team. I work for a central team in PlayStation who provide kind of game services to other studios. So we help them with hosting kind of microservices in the cloud or infrastructure or anything they need to do kind of more cloudy stuff. So we don't make the games ourselves, we help the studios who make the games. And today I'm going to be talking about one of the more interesting problems we're tackling, which is real-time game servers and how you actually go about running them in a Kubernetes cluster. So I'm going to start off with some gaming mumbo-jumbo just to get you started. And I'll start with saying, what isn't real-time? So when you're playing a game, you've got a game client. This is what's running on your console, your PC, your smartphone, whatever. And that regularly, especially these days, will talk out to a variety of services that are hosted somewhere, whether that be a data center, the cloud, etc. And these tend to be things like leaderboards, which might have time trial data for a racing game, or player content like levels in Little Big Planet. And these kind of things are often referred to as async in the industry because they're things that can happen kind of behind the scenes. It doesn't matter if they take too long to respond or whatnot, it's not going to ruin someone's play experience. These are normally either HTTP or gRPC services, and they are individual request based. That is what real-time isn't. Okay, so what is real-time? So real-time is when you have a group of players playing together. Some of you have giggled at this, so reference. This is the famous Leroy Jenkins scene. Some of you may be too young to know that. Anyway, yeah, so that's a load of players together in one shared game world is what we're talking about when we're talking about real-time. So this is a number of different clients that are all connecting to the same game server, which itself is running a kind of simulation of the game world, which is authoritative and is telling the clients what's happened. This person moved, this person shot this person, etc. The game server is the one that tells them what's going on. This is normally over UDP as a connection, and it requires a persistent connection because if it drops, you're going to get disconnected from the game, right? Which isn't fun, and it's also very latency sensitive. If there's lag spikes, you're playing an FPS game or a fighting game or something, that can be the difference between winning or losing a match. So that's what real-time is, and that is a lot harder to run in Kubernetes. The previous stuff we're talking about, just kind of HTTP, gRPC APIs, very easy, bread and butter, easy to put in Kubernetes, it works. Real-time game servers, not so much. So the three big problems, at least in my opinion, for running these kind of things in Kubernetes is these things: pod termination, auto-scaling, and how to do it multi-region. And I'm going to kind of cover how we solve each of these problems through the talk. And the thing we use to solve these is a tool called Agones, which is something made by Google. It's an open source project. You can find it at Google for Games/Agones. And it's a plugin, extension, add-on, whatever you want to call it, for Kubernetes that creates a load of first-class concepts for running game servers in a cluster. So let's start. So the first problem, pod termination. So as you might imagine, it's not very good if a pod, which is running a game server, gets terminated while someone's playing the game, as this will kick them out. So two common reasons why this might happen in the Kubernetes cluster is either the cluster autoscaler, which scales up and down the amount of nodes in the cluster dependent on load, how many pods, etc. And when it's scaling down, it'll drain a node, terminating all the pods on it, and therefore killing your game server. And the other one would be when you're doing a rollout. So you're deploying a new version of your application, the new pods come up, the old pods get shut down. Again, you don't want the old pods to get shut down if players are still playing on them. And that's one of the key problems we're trying to solve here. So Agones has the concept of a game server. And this is a custom resource definition for Kubernetes. On the screen. I'm not going to go into the nitty-gritty of every API field it has, but what the important thing to take away from a game server is it's very similar to a pod. It is analogous with a pod. One game server creates one pod running your game server. And the main difference is it has some more kind of status fields about it, which are more game server specific. I'll cover these now. So the way it works in practice is a player or machine or whatever can request a server, and they do this by creating something called an allocation request, which is another custom resource. The Agones controller then goes and finds a game server that meets their request, and it sends the information on that server back to them. At the same time, it changes the game server state to allocated. This is something a pod doesn't have. It doesn't have a concept of allocated. But what allocated means is this pod/game server is now in use. Players could be playing on this. Be careful. And then the player at the same time gets the server info back, which is normally just like the host name and the port that their client will then connect to. But this just covers how you create one game server. But realistically, you're going to be using multiple, and just like how in Kubernetes you have pods and deployments, in Agones we have fleets, and a fleet is another custom resource, and it just creates a number of replicas of game servers. It looks, again, very similar to a deployment. If you're familiar with that, you have the number of the replicas, the container image, etc. You can scale it up and down just like you would a deployment, and do rollouts by updating it, etc. You create a fleet, it creates multiple replicas of your game server, so you have multiple instances for players to connect to. But what makes a fleet different from a game server is from a deployment, is it is aware of the status of said game servers. So, for example, in this example, I've got 4 game servers. 2 of them are in an allocated state, so that means players could be playing on them, and 2 of them are just ready, and that means they're just ready to be allocated at some point. If I were to do this command, scale replicas down to 1, what it does is it will terminate the 2 ready pods, and because they weren't allocated, but the 2 allocated it will leave alone because there are people on them, so it does not want to terminate them. Which obviously is different to how a deployment will work, where you just get 1. So currently we have two replicas running, even though we've asked for 1, because it'll never terminate a pod if it's still got players on it. And that's one of the key guarantees we want to ensure, so that we're not disrupting player experiences, right? So this is how it solves the problem of, and this was the same way for deployments, just to clarify, like if you were to roll out a new version of the app, it would behave in the exact same way. It would roll out new versions of your game server, but any that are currently dealing with players, it will not terminate until they're finished, and then they can terminate themselves. And that's how we deal with pod termination with Agones. So the next problem I talked about was auto-scaling. So in a traditional cluster, you might use something like HPA, horizontal pod auto-scaling, to scale your deployment's replica count. This would traditionally, or by default, use either the CPU or memory of the pods, and it can also use custom metrics using Prometheus. But this doesn't make sense when you're talking about game servers. So if you've got a game server and it's running at 90% CPU, spinning up another game server will not reduce the load on that game server. It isn't like HTTP requests where we just need to fan them out across a cluster. Each game server has a set number of players on it, and that's not going to change, at least in most cases. So we need something a bit cleverer, something that can take more into account the kind of state of the cluster and the needs of the players coming in. And this is where another Agones resource comes in, known as the fleet autoscaler, which kind of is like analogous to a horizontal pod autoscaler. This can scale fleets up and down. This is the kind of default out-the-box version that it gives you, called the policy type buffer, you see. And the buffer just does what kind of implies. It creates a buffer of game servers. So it will always ensure you have, in this case, 5 ready game servers at any point. So if you had 10 allocated game servers, there would be 5 ready game servers. If another server gets allocated, you have 11 allocated. It would spin up another game server. So just to give you a buffer so that you've always got room for more players to come onto the cluster. However, in the real world, this is often not quite good enough. It's a bit too basic, let's say, and this is where the fleet autoscaler type of webhook comes in. And this works by allowing you to point Agones to a special webhook of your own design. So this is a service just running inside your cluster or outside your cluster. In this example, we've just got like autoscaler webhook service, which is in the default namespace. And what happens here is the Agones controller will periodically just sync with this webhook, asking it for updates, and that is what determines the number of game servers in the fleet. Now this fleet autoscaler webhook is normally a custom designed by the game team itself, because it can take into account all sorts of things like, I don't know, the time of day, what kind of players are coming in at the moment, what kind of worlds are they looking to enter, whatever they like, effectively. It's much more flexible and can be used to more fine-tune how you scale up and down your cluster. So yeah, that's how we do autoscaling in Agones. So the next thing I want to talk about is multi-region. So people are spread out all across the world, right? There are people playing in East Asia, there's people playing in America, Europe, etc. And we need to make sure they get connected to a game server that is nearby. We can't just run everything in US West 1 or whatever, because if you're in Europe and you connect to a game server there, you will have very high latency, which won't be a pleasant gameplay experience. So we need a way of kind of spreading it out geographically and having more of them. And the way you would often route people to the correct game server is using something called a matchmaker. So going back to our earlier example of Mr. Leroy over there, who got kicked out of his guild after that unfortunate incident, he now needs some people to play with, and that's where a matchmaker comes in. So a matchmaker is just something that can get together a group of random players and form them a group, right? So if you're looking for players, using a bunch of, we could do a whole talk on how a matchmaker works, but using a bunch of parameters, it will try and work out who's best to be grouped up with other people, whether that's as a versus or playing together, and then it will assign them a game server to go and play on. So it's rarely the player themselves asking for a game server, it's probably going to be a matchmaker that's going and saying, okay, I need a server for this group of players, please give it to me. So that's what I'll be talking about matchmakers from henceforth. So we can, instead of coding like, if you remember earlier, the way it works is you create a CRD called an allocation request to actually ask for one of these game servers from a Gonez, but maybe coding all that kind of Kubernetes logic into the matchmaker doesn't make sense. So Gonez provides us with something called an allocator service. This is a REST or gRPC, it does both, pick one, service that exposes the kind of a Gonez functionality as an API. So you could expose this for like a load balancer, etc. It does mutual TLS for authentication, and you can then post requests to it, and it will give you back game servers. So this allows you to have the matchmaker kind of talk to a Gonez in a more abstracted way. You don't need to have a Gonez doing all kind of CRD stuff. You don't need your matchmaker to have like CRD logic built into it or anything. And allows you to, if we're doing this multi-region, it's going to be quite useful because you don't necessarily want to expose every single one of your like Kubernetes cluster APIs to a matchmaker and doing all the security that would come with that, setting up service accounts, etc. So if you imagine this kind of what I've got on the screen here and just kind of duplicate it, that's how you do multi-region effectively, is you spin up one of these clusters with the allocator exposed as many times as many regions you want. And then all the matchmaker needs to know is I've got these number of endpoints, each endpoint, being in a Gonez allocator, which corresponds to a certain region. And then when players come in, it just goes and asks the correct endpoint for a server, and it gets given it back. So like this example, we've just got US 1 and US West 1, but just times this by however many regions you so desire. And this gives you a good way of kind of abstracting the underlying clusters away from the matchmaker and the players. This is also kind of how upgrades work in Gonez as well. So when you're upgrading an Gonez cluster running game servers, you've got to be pretty careful because you don't want to accidentally break all the clusters, break all the game servers that are running in there. So the general recommended approach for doing an upgrade with Gonez, especially if you're upgrading either the Gonez version or the Kubernetes version, is to spin up an entirely new cluster. So this is quite easy if you're using the allocator endpoint, because you could just kind of obfuscate this behind, like we use AWS, so Route 53 entry of like a gonez.eus1.com or something being representative of the EU West. You spin up new cluster, you can do canary testing on that, etc., make sure that's working, and then when the time's right, you can just switch the DNS over. The matchmaker will start sending requests to the new server, allocating players there, and the old server will slowly scale down and shut down as more matches, games finish, etc. And that gives you a relatively safe path for upgrading without disrupting players at the same time. And yeah, so that is a kind of whirlwind tour of what a Gonez does. It's very high level. It does many other things that I haven't gone into in detail. But yeah, this is the gist of it. It provides a load of different CRDs which we can use to kind of get more gamey concepts into a Kubernetes cluster, and it allows us to kind of leverage all the cool stuff that using a Kubernetes cluster would give you in the normal world. And it's worth you may ask, like, why would you do this? Why would you even try to run something in Kubernetes? I think the answer to that is a lot of the concepts we just described, like how do you auto-scale game servers, how do you make sure they don't get terminated when players are running on them, etc., is true regardless of where you run, right? If we were doing this on EC2 machines, it would be the exact same set of problems we would be facing, but we would have to have done it all ourselves. So by using Agones and how it builds on top of Kubernetes, it can help simplify that for us and give us a quite nice base platform which we can roll out across potentially all the different studios as an option for, like, here's how you run game servers in Kubernetes. Yeah, and that's my talk. Thank you.